Hi, I'm Shashwath, CEO and co-founder of Mindgrove Technologies.
Give me an elevator pitch of Mindgrove.
So Mindgrove is a fabulous semiconductor company, which is among the first to make advanced microcontrollers from within India. And what is unique about us is that we are actually doing all of the design work over here, and we actually own the design of the microcontroller completely, the system on chip completely. We
Okay.
are we are targeting our microcontrollers towards computer vision and signal processing at the edge.
Okay. So, for listeners who are not familiar with a lot of language that you used, what's fabless?
Okay,
Give first. Could we start with like a semiconductor 101? Like,
sure,
what is what's a semiconductor company all about? What types of companies exist in the world?
sure.
What's been the evolution?
Should I start with the technology?
Yeah, yeah.
Okay, so semiconductor. I mean, we use it all the time. Everything from your LEDs to your iPhone is a semiconductor, and basically, what a semiconductor is at its heart is a very special kind of a uh, material that could be a like, for example, the most commonly used one would be silicon, where it is not a great conductor of electricity. It's a decent conductor. It's not like a metal, but what it does is it is selectively conductive. So for example, it may conduct in one direction but not in another. So if you have two terminals, it may conduct in this direction but not in this direction. And what that does is it allows us, with a clever arrangement of different types of semiconductors, it allows us to create things like transistors, diodes, switches, and mostly transistors, because that then allows us to uh, chain those transistors into actually useful things like logic gates, and that forms the core of everything that we've come to know as our computing industry and our entire electronics industry. Everything revolves around this particular tiny little thing called a semiconductor.
Uh,
Now, yeah,
one quick
sorry,
question. A layperson's understanding of transistor is like a radio,
yeah,
which is obviously not what you're referring to. What do you mean
sure.
by a transistor?
A transistor is a very specific type of a semiconductor which has three layers. Um, there are two types of semiconductors, typically semiconductor materials. One is called a positive, and the other is called a negative. So, um, the most simple kind of transistor is called a PNP or an NPN, where you have a positive semiconductor which is sandwiched between two negatives, or two positives sandwiching one negative. And from there, we have a more complex one called a metal oxide semiconductor field effect transistor, or MOSFET, which is actually what we get to use in most circuits today. The older type, which is called a bipolar junction transistor, is kind of antiquated. So what this does is this device. So it has three terminals, right? Each of these elements has one terminal, and if you use one terminal as an input, you can use it to control the flow of power or current between the other two terminals. Think of a valve um, in a piping system, and imagine if that valve was also controlled by the pressure of water coming in on itself. And the more pressure that comes, the more force it allows through the other side. So that's really what it is, and it's it finds all kinds of crazy uses. The obvious reason why we use it in radios, for example, is because it's an amplifier. So you can have a switch, or you can have a valve which is very very sensitive to small currents coming in when you're taking it from the air, and use that to regulate the flow of a much larger flow of current from a battery or a mains power into your audio system. So this valve, so if the audio moves very lightly on this side, uh, on its input side, it will create a very large variation on the output side. So that's where everybody, the most well-known thing about a transistor being a radio comes from, right?
Okay, got it.
And yeah, other ways of using a transistor are as a switch. So when we use it as a switch, what we do is, if the pressure, in this case, pressure would be voltage or current. So if the current coming in is, or the voltage coming in is less than a particular amount, you don't conduct at all on the output. If it breaches a particular threshold, then you start conducting fully. So that's called a saturation mode. You're either on or you're off. And arranging transistors operating as switches together in clever arrangements, you'll get gates, which are logic gates, which are logic elements such as, you could have an AND gate, which says you have two terminals as input, and only if both of them are simultaneously on will the AND gate produce an output. The opposite would be an OR gate, where if one terminal is on and the other is off, um, any one or both have to be on, and then it will produce a true output, or an on output. If both of them are off, it will produce an off output. And then you chain all of these together to form logical elements. So when you're talking about binary arithmetic, you can create a circuit which adds two numbers using a bunch of OR gates, and what is called an exclusive OR gate. So all of these are created using the transistor from the at the lower level, right?
Okay, so essentially, computers understand binary math, which is 0 1,
Yeah.
essentially, and that
And
0 1 is represented as on state or off state.
yes. And the
And
reason that they understand the binary math, they don't actually understand anything. It's just that the circuit has been designed to produce binary arithmetic, to be able to operate in the binary domain. So actually, the very first couple of computers that were built did operate in decimal system, but then it was found to be far more efficient and far easier to program when we did it in binary,
okay, understood. Okay.
right?
Hmm.
Yeah. So now it's these transistors and putting them together that actually creates a computer. And earlier, like, when we are in college and we're doing BTech, we have electronics lab. We get these transistors which are like this big. Those were one state of the art, but now they basically used to train young engineers. Anything which is being used in serious work today would be something which is called a very large integrated circuit. What an integrated circuit means is, like, to create a NOT gate, right? Where if the input is 0, the output is 1. Or if the input is 1, the output is 0. So to create a NOT gate, you would have two transistors acting together. So that is, in this case, these are no longer the BJTs, but they're what we call MOSFET transistors, MOSFET. And there are two types of MOSFET transistors. There's a positive MOS and a negative MOS. The current technology uses both together, and so that is called a CMOS, complementary metal oxide semiconductor. And so when you actually create, like if you're creating an adder, then you would have several of these. If you're trying to add two 8 digit decimal numbers together, 8-bit numbers together, you would have something like 30-ish gates total. And that would be about 60 to maybe 120 transistors. So when you create a modern semiconductor, when you create a VLSI semiconductor, what you do is you integrate all of these onto one piece of silicon, which is the substrate. and then you actually create the circuit which you draw the transistors on top of that substrate, right? So what happens when you do that is that the circuit becomes smaller. Because it's smaller, it uses less power. Because it's using less power, it is also more efficient. And because it's smaller, the distances are smaller, it is much faster for current to reach from one end to the other, so it is much faster. So the game in all semiconductors is to reduce the size of the transistor as much as possible, and that gives you speed, it gives you power, it gives you all the things that we're used to when we buy an iPhone this year, which was twice as fast as the iPhone last year.
Okay, amazing. And so this VLSI is what we call a chip.
This VLSI is the technology that creates a chip. And so what happens is this VLSI, it's a specific technology, right? And it's a specific manufacturing process now that gets used. And basically, these circuits are etched onto silicon wafers. The current state of the art is a 300 wafer, so that means it's about 1 foot in diameter. Think of a dinner plate, and on that dinner plate, um, a modern processor, let's say a simple microcontroller like what we are building right now, that would have like a million transistors. The Apple M1 chip or your typical Intel chips would have upwards of a billion, maybe close to 10 billion kind of
Wow.
transistors. It's enormous.
And that
So
fits into what size wafer?
typically, so the wafer is 300 in diameter, and typically you have chips. Chips could range anywhere between 2 square mm, 1 square mm. I've heard of even smaller than 1 square mm, all the way up to behemoths like the Intel Xeon, which is rumored to be something like 800-ish square mm.
Okay.
So now what? Now it's actually the manufacturing process that comes next, right? So what they do to manufacture this is they create a um, this is called photolithography. So you have a base silicon, and then you draw the circuit as a mask that is like a die, and then you use ultraviolet light to expose the silicon. Wherever it is exposed, um, it turns from silicon to silicon dioxide, and that can be etched away using acid. And then on top of that, you grow a little bit more material, and then you etch again, and then you add more circuit, and then you etch it off, and then you add more circuit, you etch it off. You grow it in layers like that. As you grow it, the circuit builds itself. And like I said, there is an eight. Let's say there is a 10 by 10 chip, right? That's 100 square mm. So you'll have a 10 by 10 mask, and the 10 by 10 mask will be put into the UV photolithography machine with the silicon wafer coming under it. It will keep etching each. So each layer will have its own mask. So it will etch each mask. Could be anything between 50 and 100 layers, depending on the chip and the complexity and so on.
So
And
it's
yeah,
like 3D printing.
it's more like CNC than 3D printing.
Okay.
But the printing industry is a very good analogy for the business of semiconductors, and I'll get to that. So once this is done, you have these 10 by 10 squares on basically edged onto a dinner plate, and then we cut it kaju katli style. We cut it like that. It's called dicing. You cut it using lasers, and then you get these 10 by 10, 10 by 10, 10 by 10 little wafers. They're called dies. And these dies are the actual chip. After you get the dies, you have to package them, typically in either metal, plastic, or ceramic. And then you have the little metal leads that come out of it, or the metal balls that go on the bottom. And that is a chip that everybody can recognize whenever your electronics breaks and you see the chips inside. That's actually what it is. usually the packaging is much bigger than the chip, right? So, and depending on the packaging, it could be much bigger or several times bigger. And there are various packaging technologies. So, once you package it, then it is taken out, and then you put it on a PCB and you solder it, and then you actually, with all the other components that go onto that particular board, and then you get what you would actually think of as, let's say, a computer or a phone or whatever. Now, this entire process which I have described to you happens through multiple entities, multiple companies, multiple countries, multiple agencies, multiple disciplines, because it has everything. All of this etching and growing and silicon, all of that is hardcore material science. It's hardcore chemical industry, process engineering, which I have only a very peripheral knowledge about because I'm an electronics engineer and my skill is in design. So, taking the die, the raw silicon die, and then packaging it in that plastic package is a specialty all by itself. And so there are agencies which do this, agencies which do this, and then there are agencies which do the design. So what we have now in the landscape is you have the design company on one end who's creating the design, and then they send it to a semiconductor foundry, which is where the wafer is taken and etched. And then the foundry gives you bare dies, typically unpackaged dies. Then it is taken to an assembly, testing, marking, and packaging company who does assembly, which is putting it into the package, testing. So they take that package, they put it into a testing machine and check whether the circuit is actually working per spec. Then they do the markings on it, and then they sort it by functionality, whether it's that's where you get your different speeds of computers from, right? They do the marking, and then they
What do you mean
package
by
it,
marking?
making markings on the chip,
Is it
on the
just
package.
like, is it like writing a label, essentially, just putting a label on it?
Yes, yes,
Yeah. Okay.
but it's enough of a specialization that it gets its own name.
Okay. Okay. Hmm.
And then packaging. Packaging is where you where they put it into a tray or a reel of like 100, 1,000, 10,000, 100,000 chips, and then they
Okay.
ship it out.
So each chip is individually tested by them.
Yes, it should be.
Okay. Okay. Hmm.
But the tests at this stage are very rudimentary.
Hmm.
So now, a company like Intel has all of this. Actually, only Intel today, among the major companies, has all of this in house. Design, manufacturing, packaging, everything is in house, right? So, there were other such companies in the past, but either they have all shut down or they have split up. So, this is called an integrated device manufacturer, IDM. I think Intel is probably the last man standing of the lot. There are a couple of others like Texas Instruments, which have their own foundry for some lines, but not for everything. Everybody else, right? AMD, Nvidia, Qualcomm, Broadcom, MediaTek, us. Everybody else is called a fabless semiconductor entity. So the fab here is the fabrication unit. We do not own the fabrication unit, we only own the design. And then we send it out to the fabrication unit of our choice. You have to work with them very carefully to adapt your design to their process and get it out from there. Then you give it for packaging. Packaging is another company. So it's become a very diversified, a very open kind of an environment where different people can play at different levels.
So the fabricator companies, I believe the biggest one is the Taiwanese company called TSMC.
Yes,
I guess
by
most of the
by
world.
like a crazy margin.
Mm. Like the Apple M1, M2, M3 chips, the Google
So
chips,
all of
all
Apple
of
chips,
uh,
most of Qualcomm's chips, most of Broadcom's chips, most of MediaTek's chips. So that's all of your cell phone. Um, AMD and Nvidia are all their biggest customers, and they are the ones who keep pushing the boundaries. So we measure the size of a transistor in nanometers, right? And they are the ones who keep pushing the boundaries: 5 nanometers, 3 nanometers, 1 nanometer, zero point 0.5, 0.18.
wow. Okay.
So they're very so one of the things about TSMC is they give you a guarantee that they will never do a design, so you can be sure that your manufacturer will not be competing with you. So
Why was
yeah.
there a need for this to become specialized units, like a specialized fabricator and a specialized design house? Is it that there is too much complexity and it's best to specialize?
Yes, pretty much in a nutshell. So what happened is, as the technology became bigger and became more and more complex, two things. One is it's become so complex that you need to specialize and you need to create something which is very focused on either this part of the problem or that part of the problem. If you try to mix the two, it becomes a mess. Um, Intel found that out because they failed in their post 7 nanometer process. Was They did not get the yields. I will talk about yields later, but they were basically not able to make it economically work. What happened is, for a fab to actually be making money, it needs to run 24/7, and a small foundry, a really small foundry, would be making about 40,000 wafers per month, right? Well, taking 40,000 wafers into production per month, it may take about 3 months to actually manufacture. A large foundry like TSMC has a volume measured in several million wafers per month. So if but a single company, let's say Mindgrow, would not have that kind of volume definitely to start with, and probably never in their lives would they be making like 40, 50,000 wafers a month. So it's it's really hard for us to own our own foundries, and therefore this particular model of an outsourced foundry and an outsourced assembly uh, house, all of that came up. But as you can see, all the names that I mentioned, right? Nvidia or AMD, these are the big names in the semiconductor industry, which are household names, and they're huge market cap companies. So a lot of the value is actually aggregating to the design and not to the manufacturing. The foundry margins can be relatively low, whereas design margins can be relatively high. So that's basically what it comes down to. It's very hard to do foundry unless you're aggregating several designs, and it's very hard for. I mean, the process control is nuts enough that I mean, you're talking about things happening at the scale of a nanometer. So you're talking about something which is so hard to control. So naturally, it aggregates to a few strong players who can actually get it done. And the biggest of that, as you mentioned, is TSMC.
Yeah, you had mentioned that the chip making and 3D printing analogy. You wanted to say something on.
Not 3D printing, I would say more like the publishing industry.
Okay.
So imagine, like, there's an author who writes a book, and then he takes it to a publisher. Now, what the publisher does is the publisher does the copyright or artwork, puts a cover on it, editing, copy editing, all of that, and then does not necessarily own a printing press. So they give the print, outsource the printing to somebody. Probably the binding happens elsewhere. It's packaged, it's distributed through various different channels. The actual author and the publishing house would be, in the analogy, something like a fabulous semiconductor entity.
Okay, got it. Okay, okay. So, what is the gap in the market which you saw, and like what made you start Mindgrove?
So, what made me start Mindgrove is not that I saw a gap in the market. What made me start Mindgrove is that I wanted to run a company. So
Okay,
that
okay.
the process is slightly different, right? Mm. And we looked around for what it is that we could do. Well,
Oh,
the
who's
thing,
we here? Just give some context here.
so sure, my co-founder is Sharan, and we were colleagues in the previous job.
And what is
Well,
that?
actually, I was a senior to begin with, and then we were colleagues. So we were working as software developers for what is called non-destructive testing, and that is where you use stuff like ultrasound, X-ray, for industrial purposes, like for testing a plane. And what happened there is, I'm a hardware engineer, and I wanted to always make my own hardware. I did not want to be a software developer for somebody else's hardware. I wanted to make my own hardware, probably my own software also. So I looked at doing that. And one of the gaps that I found over there is that I could not find a processor which is conducive to the kind of things that I want to do. Either I have to settle for something which is expensive, um, which is a poor fit. It's expensive because then that's the only thing that gives the performance I need. But in terms of other features that I would need for these kind of domains, it's a poor fit. Or I would have to chain together a bunch of half integrated little cores and then write a million different programs to actually make anything work. Um, so,
What is this
yeah.
use case that you're talking about for which you did not find a
Well,
customer?
in that case, it was ultrasound.
Okay. So a chip to control the ultrasound machine.
Yeah.
Okay.
Which is a
Okay. So
processor, basically. It's a processor with special interfaces. That's all.
okay.
And, well, the other thing is, in the place where we were working, we never got an opening to do this kind of research and development and actually create the product. So during the pandemic, we just kind of decided, why don't we try it on our own? So we came out. Ultrasound and X-ray, especially industrial, is a tiny market. So we tried to think of doing radar because there's a lot of different applications you have for it. And so by that time, Sharan had already started his part-time PhD at IIT Madras. His guide was Professor Kamakoti, who is also an old family friend of mine. And we would keep meeting him, and we mentioned to him that we wanted to start a company. We wanted to do this. He said, take and use Shakti. Uh, well, we had known about Shakti since about 2017. Again, because
And
it's,
what is
yeah,
Shakti?
I'll come to that. So the interesting thing is, I'll just take a digression and come back to Shakti, right? Just talk about the landscape as it existed. So the interesting thing is, there is about 20% of the semiconductor workforce, especially the design workforce, is in India. They're Indians working in India, either out of Chennai, Bangalore, Hyderabad, Pune, a little bit in Noida, I guess. Um, and a large portion of the demand, though it's not visible because a lot of the chips get ordered outside the country and assembled outside the country, and you get finished products shipped into the country. A large portion of the demand is also here. I would say about 15 to 20% as it stands. Huge market for India,
15 to
right?
20% of global demand of chips is
Global
in
demand
India.
of chips would be in India, yes.
Wow. Okay. Why is that? Because of the mobile revolution
Well, mobile revolution is one
and
thing, but it's
IoT.
not just that.
IoT.
You have IoT, you have, well, your LEDs are chips.
Ah, okay. Mm. Any smart
So
device, basically.
any device, any electronic device today is a chip.
Mm.
If you have, let's say you have an LED with a dimmer, right? In the old days, when you had a light with a dimmer, the dimmer was a coil which you turned. Now it's a coil which you turn that is read by a very tiny processor, which then generates a signal for that LED to reduce its. So it's a lot more complex, but it's just easier to do it rather than building a bunch of analog electronics. So that's why we do it that way, right? So um, Shakti was born out of this. We don't own any of the IP in India. Um, it's all of this 20% of the workforce is working for MNCs. Their IP is owned outside. And Professor Kamakoti and his students wanted to do some security research on a processor. They approached um, ARM. ARM is one of the biggest suppliers of processor IP in the world. Um,
So,
they,
ARM is an interesting stakeholder in this ecosystem that we did
oh
not talk.
yes,
What
oh
is ARM?
yes.
Uh, where does ARM
So
fit into this ecosystem?
now you're dragging me into a rabbit hole called IP. Now, design itself is such a vast ocean that you can't. I mean, nobody designs the entire chip in their own little fabulous semi or even very huge fabulous semi company, right? Not even Apple does it. So, different parts of the chip you might assemble it using IP from different people. One one of the biggest suppliers um, is ARM, and what ARM supplies is different kinds of processors. Specifically, what they supply is different kinds of mobile processors, and they have something like a 99-ish% stranglehold on the smartphone, especially the smartphone industry, and maybe about 98.5% of the total cell phone industry. It's
Wow.
right. And so if you have an Apple phone, all Apple iPhones, iPads, MacBooks, even Apple watches are using ARM processors inside.
So, ARM processors or the designs from
Designs
ARM,
made by ARM,
right?
which is the processor IP, which is integrated into the rest of the Apple chip.
Yeah, in a way, it's like how if today you want to build a website, you will just use WordPress. You will not build it
Yeah,
from
but
scratch.
well, that's a good analogy. And if I can go back to the publishing analogy again, um, imagine that it's a multi-author book, and each author is writing a chapter. So the chapter called Processors would be written by ARM.
Okay.
It's not that simple, especially if your name is Apple. So what Apple does is they license the processor and then they tweak it.
Hmm. Okay. Okay.
Um, so companies like Qualcomm or MediaTek, all of them also use the same ARM processor,
Hmm.
and a lot of ARM also finds its way into these small IoT kind of devices. If you've used, you know, um, probably all your modems, Wi-Fi routers, all of them, they might have an ARM processor in them. The classic um, version of the processor that you see in cell phones is called the A series, and the one that you see in real in small microcontrollerish applications is called the M series. So you get A57, A72, A whatever, A76, and then you get the M0, M4, M33, M55. So they have their different lines.
Okay. Understood. Right. So coming back to Shakti,
Yeah.
which is where the rabbit hole of ARM started.
Yes. So we'll come back to Shakti. Picture yourself in 2012. ARM is one of the biggest suppliers already. Not as much of a bully monopoly as it became later, but then already pretty much the biggest skin on the block when it came to mobile. Uh, so they wanted to do some research on the processor, and to do that, you actually need to take the processor and start making tweaks to it, like what Apple would do. ARM refused. So the IITM team said, "To hell with it. We'll make our own processor." And then they looked at a particular. Now I have to go into another rabbit hole called the instruction set architecture, right? I'll try to make this as small as possible because I don't want to drag this. So an instruction set architecture is like a specification for a processor. It is how the processor itself interacts with the program, or how you write a program for that particular processor is called the instruction set architecture. And ARMS is proprietary. They developed it themselves starting in the 1980s. They had a major revision in the mid 2000s and the late 2000s. So we're on version 8, version 9 of the ARM ISA. Similarly, Intel and AMD share ISA called the x86 that comes from 8086, 80386. If you're an old timer, you will remember these numbers.
Yep, yep, yep. My first computer was a 486. I still remember.
Yeah, mine was a 286, so yes, we all remember those. But that's where that comes from. The X is the 80x86. And AMD was licensed by Intel to use the same instruction set architecture. Um, there were other licensees at different periods of time. I don't think there are too many more anymore. Anyway, so x86 is another well-known one. Another major one is called the IBM Power. And if you remember, Apple used the IBM Power before they switched to the Intel process in like the late 2000s.
IBM used to be a chip maker.
IBM used to be everything.
Okay, okay, okay.
IBM used to be IBM research is still cutting edge in terms of chip making, but then they only do the research.
Okay, okay, okay.
So IBM, Apple, and Motorola together came up with this thing called Power PC, and that was there. When IBM kind of started exiting making chips by themselves, so Power is still being used in IBM servers. They make their own chips for their servers sometimes. Though of course now they're all now hilariously IBM is also a fabulous semiconductor entity. We can come to that if you want. Um, so IBM open sourced or opened out in a kind of a way. It's not exactly open source in that sense. Their power architecture, and that was very well known. So the first idea was to make a processor based on the power architecture. They took one look at power, and it is exactly like something that you would expect out of a behemoth like IBM. It's too complex to implement. Right around that time, in Berkeley, in the US, uh, the guru of microprocessor design is a professor called David Patterson. So every computer science engineer who has ever read computer architecture will be familiar with Hennessy and Patterson, which is the textbook that we all use for that. Hennessy is Jack Hennessy, who is now chairman of Google. And so Hennessy and Patterson, working at Berkeley, um, built, they came up with something called a reduced instruction set computing architecture. This is in the 80s. ARM follows a reduced instruction set architecture. Um, Intel, on the other hand, x86 on the other hand, is what is called a complex instruction set computer, CISC. So, a major debate that raged in the 80s, 90s is, excuse me, CISC versus RISC.
Who
Ultimately,
won?
the answer.
Who won
Sorry,
the debate? Who won that
no,
debate?
stalemate.
Okay.
So the biggest risk that you know of is x86, and the biggest risk that you know of is ARM, and each one is dominating a market. So there is no winner. There's no clear winner. What we figured out is that CISC and RISC don't matter after a point. The underlying microarchitecture matters a lot more. But anyway, so there were several iterations of the risk uh, philosophy, which were made as research processes inside Berkeley. Now, Dave Patterson's student Krista Astanovich and his team was starting to build what they called Risk Five. And what they did is they from the start they open sourced it, so anybody can download the spec, and they'll provide you references and all kinds of other things, and then you can royalty free you can just use it and build your own processor. That's what the Shakti team did. So turns out that after Berkeley and MIT, Shakti was the third team to actually implement it,
Okay.
and that is purely Indian owned IP. It is IP coming out of IIT Madras, and it is IP coming open source, so anybody can take it and use it. And especially a company which happens to be well, its mentor happens to be the creator of Shakti, so we got privileged access in terms of talking to the people who originally built it. And Sharon is a member of the lab, so we know it very intimately, so we started using it. So jumping back out of all the rabbit holes, we are sitting in Professor Kamkoti's office, and he says use Shakti. And I'm compressing a lot of conversations that happened over like 3 4 months over here, but basically the conversation went something like this: sir, we can use Shakti, but is the chip going to come out? Yes, of course the chip will come out when you make it. So uh, you do realize that I don't have $1 million, $10 million to sink into a semiconductor startup? Yes, I know that. IIT Madras will support you. Get yourself incubated. um, So just at that time, they started something called the IIT Madras Pravartak Technologies Foundation, which is our incubator. And what Pravartak did for us is they're a technology innovation hub. So one of the things they do is they incubate startups. So what Pravartak did for us is that Pravartak gave us two very important things. They gave us a discount on third-party IP that we need to build the chip, which would be insanely hard for us to build internally. And even if we built it, it would be equally hard for us to get it certified as working. And you're not going to be able to sell a chip which is not certified that way. And the second thing they did is, even more importantly, they gave us tools. The software tools for semiconductor design can run into, well, 3 4 times the typical seed round that a startup might raise. So the only way that semiconductor startups are possible is by some kind of an aggregation mechanism for these tools to be made available to them. Pravartak was among the first in the country to do it. We were the first beneficiary of that. There are a few others like FabCI in Hyderabad and Safel in Bangalore, which do the same thing. Um, the cost has not gone anywhere. We have to pay them back once we actually start selling chips. But at least it's not front loaded on top of the company, and you can't actually build anything. So uh, that is basically how we got started. The third thing that IIT and Pravatak did for us is there will always be a lot of people know about Shakti, right? And there's always a lot of questions coming to the lab as, when will Shakti be available? Can I use it to build a mobile phone? Can I build it to use it to build a electricity meter, can I use it to build a toy? And the answer was always blink, because I mean IIT Madras is a research organization. It's a educational institution. Its job is not to commercialize IP, and all of those queries got directed to us. We looked at all the different things that people wanted to build. We looked at the markets. We looked at the um, volumes. We looked at the complexity of addressing that particular market, and we settled on chip number one and chip number two, which we have designed slash are designing. And there's a lot of reasons why we settled on these things, right? I could build anything. I could build a server grade processor. I could build something for the mobile phone industry. I could build something for uh, desktops and PCs. But couple of things over here. One is you need to build a chip which you are actually capable of building, which the team is actually capable of building within a reasonable amount of time. I could build a server grade chip in about 6 or 7 years. I wanted something that we could build in a year or so. It needs to have a decent market, and it needs to be something, it needs to be a measurable success. So we scouted around for different markets, and one additional constraint that we placed on ourselves is stick to what you know best. I know signal processing, I know machine vision, and I know what all these things involve. Um, I did that for 15 years, so let's build a chip that I would find really great to work with. So that's how chip number two was actually born. But then as we spoke to people, they said, that's too complex a spec. You're talking about this and that IP and this IP. I don't want to pay for all of that. I don't want those kind of peripherals. I want something that I can put into a meter. I want something that I can put into a small, embedded device. It still has a lot of processing that it needs to do. It needs to, in some cases like battery management and stuff, it needs to actually run a small neural network. But I don't need anything more than, I need basic stuff on the outside, and I need some decent performance. What I have on the market are things which don't have that kind of performance that you're talking about. So I'm very interested in the performance that you're giving me, but at hmm, not with the kind of spec that you would use for machine vision. So we asked, what's the volume? The volume was very interesting. So we said, okay, that we can do. It's a fork on the road to the second chip anyway. So we'll build it. And that fork has taken us about a year to build. We literally got started in, so we got started with the concept of the design in about November 22, and we actually started work on the design itself like April 4th, April 5th, 23. We taped out on November 15th. Tape out is the technical term for when the or industry jargon for when the design goes to the foundry and they start manufacturing. So we taped out the prototype run on November 15th.
Oh, which is
Um,
just like a week back.
it's just like a week back. This is only a prototype run. So we have to get it back. There's still like months of wait time before we actually get it back and we look at it and see if it's actually working. We may have to do another prototype run to actually fix bugs and so on. So we have a few months wait before we can actually launch the product. I don't want to. I want to emphasize that it's still a prototype run, and we're not out of the woods yet with that product. Um, but it's still nice. It's a nice closure to a lot of design activities that happened, and so we did that, and then we've gone back to building the second chip.
Okay. I have a couple of questions. why did you need to design a chip? Shakti was a chip design, right? Like a open source chip
Oh
design.
no, no,
What
no, no.
was? Okay.
Shakti is a um, bunch of IP.
Okay.
More to the point, Shakti is a core. So it can't do anything by itself. It can't be a chip by itself. You need to do two things to have a chip, right? You need to have peripherals, so things to connect to the outside world. The Shakti core does not have that. There are some peripheral devices which were developed at IIT Madras, which you also used. And the second, the most important thing that you need to do is you need to pick a foundry and you need to adapt the design to the foundry. You need to characterize it, qualify it, make sure that the design is working correctly. You have to simulate it and all of that. So, if you think about it, one of the biggest semiconductor companies in the world, Qualcomm, uh, a very disparaging way of dismissing what they do with processors is they uh, buy IP from different people, from ARM, from this guy, from that guy, from that guy, and they just put it together. Just put it together is massive amounts of work.
Got it. Got it. Got it. Okay. Okay. So, what all did you put together? Where did you get the instruction set from?
So it's Shakti. So the
Shakti is
instruction
the
set is
instruction.
RISC-V.
Okay. Okay. So
And
Shakti is the
yeah.
instruction set. And where did you get the design IP from?
So the other rest of the IP, some of it was from IIT Madras's own IP, which they did for testing and qualification.
Okay.
By the way, Shakti has been fabbed out before at least four times
Okay.
by IIT Madras itself.
Okay. Like prototype
And one
runs.
of those was at a very advanced process node called the Intel 22 nanometer process node. Intel sponsored that chip out.
Okay.
And so there's a lot of IP that was built for those tape outs, and there's a lot that was built for simulation and stuff like that. So many of the peripherals came from there. We made lots of modifications to them. We fixed some bugs. We adapted it to things that we wanted to do, and so on. So that is Shakti itself, and some of Shakti's. And then we bought some other IP, most critically the clock, which goes into the chip. All of these chips are clocked, right? That's where you get your gigahertz number from. And by the way, our first chip is clocked at 700 megahertz, which already makes it something like nine times faster than the um, 486 that you used.
Wow. Okay. Hmm.
So this is a 700 megahertz chip. So we needed a clock for that. If you can use an external clock, but then you can't usually breach about 300 megahertz if you do. Um, the chip, the memories that go, the RAM that goes onto the chip, right? And the RAM is not only what is accessible to the program. There are other bits of RAM scattered around the chip for doing various things. That is provided by the foundry. So we had to create that, and we had to get that, create, adapt it for the design, and then put it into the design. Then the clock we bought from outside. We bought an
And the
analog to
clock is
digital
again a
converter from
piece
outside.
of code.
Yeah, you could say that.
Okay.
It's a circuit design.
Okay. 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 Got it. Hmm.
So the way we design these circuits, right? We write code, and then there is a compiler that converts it to a design. It's too complex to actually do these kind of circuits by actually drawing the circuit diagram. It won't work. So we write the code, and then the code gets the code is in special languages called a hardware description language, and then that gets transformed into circuit. And that circuit, so it's under supervision. It's not completely automated. That circuit has to be tested, verified, qualified, all of that. And then that circuit has to be laid out in silicon. So we create the manufacturing design for that.
Like the various like it is
Each
multiple
layer.
masks. Each layer. Okay, that's
Each layer gets its own mask.
okay. Okay, so you design each of the masks. Okay.
Well, no, we don't design each of the mask. We design the layers.
Mm.
The actual design of the mask, layer to mask, is something the foundry does.
Okay.
And the reason that the foundry does it is because it's very specific to their process. And they will actually use an electron beam to etch that mask. So the processes here are they all sound like science fiction, right? Just one more aside over here, just because I said science fiction. Let me tell you this one aside on the technology that goes into really advanced chips like the M1, M3, not even M1, like M3 and all of that. The latest series of AMD Intel processors, the latest Nvidia GPUs. There is a company in Netherlands called ASML, and
ASML is a vendor for TSMC, right? Like they
yes,
provide the
they
machine
provide the
with.
photolithography machine.
Hmm.
Each machine is like $600 billion, $600 million or $700 million or something like that.
Wow.
It requires like 10 747s to transport it from the Netherlands to Taiwan.
Mhm.
It takes a bunch of time to assemble it. And basically, what this machine does is it produces light of a very specific frequency. And the way it does it is there is a chamber in which there is a drop. Tungsten is melted and made into drops. As it's dropping, a laser hits it once to take a circular or teardrop shape and make it into a kind of a concave shape. And then it hits it again to convert it into a plasma. That plasma gives out light in several frequencies. Out of those several frequencies, one particular frequency is filtered. That filtered frequency, is too small to be focused using lenses. So they have these special mirrors, which are the only thing that it actually interacts with, um, to bounce it like a concave mirrors, like a funhouse mirror. Bounce it, bounce. Each time it bounces, it focuses a bit more. Then finally, it ends up the size of the mask, and then goes and illuminates the chip. So, I mean, that's the kind of technology that these people are talking about.
Yeah, incredible. And I read about this company because I believe US kind of told them that they can't sell their machines to China.
Yeah.
Right.
So, ASML is currently a monopoly in the field of extreme ultraviolet. And like I just explained, it's extreme. ASML is a monopoly not because of any other structural reason, it's simply because everybody else gave up.
Amazing. Amazing.
So there are other companies which can build like older process nodes, right? Uh, Nikon, Canon, Applied Materials, Lam Research. There are all kinds of companies which can do other processes. These extreme ultraviolet processes, currently ASML is the one vendor in the world.
Okay. Interesting. Mm.
And so the thought is that if they prevent ASML from selling, and ASML, even though it's a Dutch company, it uses a lot of American IP. So the American government has a certain stranglehold over what they can and cannot do.
Okay. Got it. So, which fab are you using for your prototype run?
Um, I will tell you that it's in Taiwan, and NDL prevents me from saying any further right now.
Why is there an NDA? Why would a vendor ask their customer to sign an NDA?
Because they don't know if the chip will work yet.
Okay. So
They
they
don't
don't
want to
want.
get out ahead of it and say that they always prefer. Most of the foundries always prefer to sit in the background. I mean, unless you're a industry insider, well, now a lot more people know because of all the um, noise being made about it. 5 years ago, had anybody heard of the name TSMC?
No. Yeah, it was
And
an unknown company.
it was an unknown company which even then made something like 60% of the semiconductors in the world by value. Mhm. By shipments, it's probably a little less.
Okay, okay, interesting. So, and what is uh, what kind of customers are you making this for?
So we're making this for people who have, you know, people who are doing electronic designs, embedded IoT kind of electronic designs. So we're talking to people who are doing biometrics, the biometrics that let you into your office. We're doing it for people who build smart meters, energy meters, water meters, those kind of things. That's the first chip. All your connected devices in your house. So one of the things we do is we built in security into this chip at a level which is not typically available on microcontrollers. And the reason is that these are all things that are you would never have thought of connecting to the internet even a couple of years back. Now you're connecting them to the internet, and they are a security hole. So if you can provide encryption, if you can provide those kind of security features over there, um, makes it easier for uh, total system security.
So your pitch to the manufacturers or the device manufacturers who will use your chip is that it's a made in India chip A, and B, it has more security.
Um, actually, for a lot of things, those pitches don't work, right? It is, um, but they do exist, of course. It's always there in the background that it's a made in India chip. We aim to be world class in quality, and we are always measuring our quality against the top in the world in this class, which is Texas Instruments, NXP Semiconductors, which used to be division of Philips, and Renesas Electronics in Japan. The fourth is Infineon, but then they're a bit more known only for automotive, so it's not so easy to measure against them. Um, so we aim to measure ourselves against that. We're not trying to just. I mean, we're trying to cost optimize, but we're not trying to cost cut. So there are security reasons why you may want a made in India chip, but you may also want, like, for logistical reasons, you would want an Indian supplier, right? So that works a lot. Um, that is one pitch. The second is, yeah, like I said, one pitch is that you get the highest quality at a decent discount, and only of the features that you need. You don't need for most of these kind of applications. You don't need all the features that the top end would give you. So I'll cut some of the features and give you a discount. The second is the next one is security. And the promise here is that we give you security off the fly without actually charging extra for it, and in a way that you can actually use it without making it too difficult on yourself. The next one is support, which is something that we give from within India. So that's important for a lot of people.
Support for the developers to
Yes,
write their code that will interact with the
both software developers and hardware people,
okay.
right? We give you reference designs, all of that.
Hmm. Okay. Okay. And what is the what's the way in which what's the go-to market for this? Like, uh,
Mm, in a sense, we've already gone to the market. We've been talking to a lot of people, and the way we do it. So comes to our philosophy, right? We want to be a product company. We don't want to take projects, but then it has to be something, a product that will actually sell in the market. So what we do is we study the market and we create a proposed solution. We call it a 60% spec. Then we shop it around to people, ask them what they think of it, and like show them how their product would look with our chip in it. And then we ask them questions like, does this look doable to you? Does this look worth it to you? um, what other kind of acceptance criteria do you have? Is there anything in here that you absolutely need, which we haven't put in? Or is there anything over here which you think is redundant or irrelevant and you want me to take it out? And what we do is so it doesn't make sense for us to develop one chip per vertical. You won't get volumes. So if you want to get volumes, what we do is we design a chip which is flexible and adaptable to situation. And we also have a flexible model of working with people where we can either just give you the chip if, well, you're a company which has that kind of a design shop, hardware design shops, or we will give you a reference design and you can write your own software for it. So we um, we own our own spec, and if something is not possible in hardware, we do it in software, or rather it's software first. It's software driven. If something is possible in software, you do it in software, and you do stuff in hardware to make the life of the software developer easy, and not just because you can do something in hardware. So um, there are all kinds of little things over there where we talk to customers, and this chip has been designed with a whole bunch of inputs from a whole bunch of people, and all of them are interested. As soon as they get samples, many of them are ready to place orders on us.
Give me an example of something which can be achieved through both hardware and software, and what would be the way in
Huh.
which you achieve it through software instead of hardware?
Okay. So, very, very simple example, right? Let's say that you have we're talking through mics and speakers here. And let's say that you know that there is a particular hum at a particular frequency and you want to cut it off. You could do that in hardware. You could actually do that at the mic level by adding stuff to the mic. Or you could do it in hardware by building an analog circuit with a bunch of transistors to do it. But um, for a DSP engineer, it's always easier to just take the entire thing into the system into a DSP chip, convert it to do a Fourier transform on it, apply a filter, and then Fourier transform it back. The hum is magically gone.
Okay.
And the advantage of doing it in software is that tomorrow you want to change the frequency, you can change the frequency easily. More importantly, tomorrow if you want to change the exact algorithm, I don't want Fourier transforms anymore. I want to do something more complex. I want to do machine learning on it. You can do machine learning on it. There's nothing stopping you. So what I would do there to accelerate it in hardware is, if I'm doing a Fourier transform, right, there is a particular element called a multiply accumulate, which is the heart of a Fourier transform, fast Fourier transform today. You build a bunch of multiply accumulate units, and whenever the programmer encounters that point, instead of writing the code for it, he'll just call the multiply accumulate unit.
Okay.
It's a very,
Okay.
very trivial example. I mean, that's very old. But then what we do in terms of software driven code design is a lot more, is along those lines, and it's a lot more complex.
Okay. So your value add to a customer is that you are not only an like a India supply chain vendor, but you will also help them to design. Uh,
Yes.
that is something which a foreign chip supplier may not necessarily help them to design their
Yes.
hardware and software.
So a lot of these people, right, they don't use the top end of the market. They use other chips. Just put it that way. And they do that typically for cost or other supply chain issues. And you often find in that kind of a market that there's no documentation, or It is made needlessly complex for the user because it would have made life marginally easier for the designer. The documentation is in languages that you don't follow. There is no support. The support forums are empty, or just filled with questions. What we can guarantee is that we are there
Okay,
and we'll help you
got it.
build it.
Got it. Who certifies that a chip is ready for sale? Like you said, that there is a cost of getting a chip certified.
So not exactly certified to that the chip is ready for sale. Uh, so if you're claiming anything security, then there are certifications on security. Do you have the stuff that you claim? Then there is certification for temperature uh, sensitivity. So, like if you're, for example, if your chip is going to go into the engine compartment of an internal combustion engine vehicle, it needs to be able to handle like 125 degrees Celsius. Um, if Then there are certifications for safety, as in can it recover from a fault, and you have to have documentation to prove that. That is called functional safety. That is very important in like the aerospace industry, in the automotive industry, wherever life is involved. You have functional safety. So there are these kind of certifications that you would typically have to do. Electromagnetic interference is a major certification that you would have to do, depending on where you're in deploying it. So all of those things.
And there are separate agencies for each of these type of certificates.
Yeah,
Okay.
and annoyingly, not enough of them in India.
Okay. Okay. So you have to send it out for some of the
Yeah,
certificates.
we'll have to send it out and get it done.
Okay, okay. So the reason why it takes 10 million to start a fabless chip company is the certification cost, the cost of the software which you need to
Yes.
use to design the chip,
Yeah.
the cost of people, and so on. How much have you raised till now?
Which raised 2.33 million.
And
That is enough to make one chip
okay,
and go to the market and see whether the chip will stick.
okay. I- is there a working capital requirement here? You'll have to pay your uh, fab in advance, like if you order, let's
Yeah,
say.
for the it's not that much for a production for a prototyping run. When it comes to production runs, yeah, it'll go into a nice, very very significant chunk, and we will have to find out a way to raise that.
Right. So you before you actually are able to sell, you'll need to raise more money, right? Because you need the working capital
It depends. So if we have enough orders, we can raise that easily.
through debt or something like that, like or
Yeah,
based. Okay.
yeah, through
Okay.
debt. No, just raise another round. I mean, if we raise a substantial round, we can use it to finance, go to market for the first chip. We can use it to finance part of the second chip.
Hmm,
There are a lot of other things that we can do. But
hmm,
then what we're waiting for is to get the first prototype out,
hmm,
get a little bit of market traction, like tentative orders or something, and then that's enough for us to actually raise a decent amount of capital.
hmm. What would be the next raise like? 10-15 million types.
Possibly. I mean, I'm not going to give you any direct numbers because we're still working on it. Frankly, the answer there is I don't know, because a lot of it depends on two three things, right? One is how many orders we get, how soon we have to ramp that production up. Another is um, how much of the second chip we want to finance in this round, or do we want to raise another round for that. It depends on how how many extra tools or IP that we will need to buy, because we get a decent set now, we get almost everything right now, but then there are certain things that we can't do with our current tool set. We get limited number of licenses, so there are a lot of other considerations that we have to go through to understand what is this we want to do. Um, so one of the main things is right now, since we have Pravtak's backing, a lot of that cost which we would have to raise could go into hiring great engineers rather than circling uselessly around IP and tools. And a couple of really key engineers, right, can make all the difference in chip design. It's so we have this thing called a front end or back end design team. So the front end team is what actually designs the logic, and often these guys can be rock stars. The back end team is the one that transforms the logic into printable circuit, and they're rock stars of a different kind. They're rocks. They're very patient. You need to be very patient with the tool. The tool will give you all kinds of stupid errors. You have to be very patient. You have to be very methodical. We are fighting against companies like Nvidia and AMD when we're hiring these engineers. So yeah, they cost a lot. And Apple,
But the good thing is that because India has a pool, so it's not like
yes,
this kind of talent is inaccessible.
it is not inaccessible. And frankly, there's a lot of other things that we've learned. A large portion of these skills, you don't need to hire the top talent. You can hire mid-tier and train them up. And there are things that I would like to call force multipliers, like, for example, the specific tools that we use. We inherited a tool from the Shakti team called the BlueSpec System Verilog, which is a hardware description language, which is very high level on one side, in the sense that you can just specify something and then not have to worry about each individual wire. But then it still feels a lot like actually designing hardware and not writing. So a lot of these other high level languages are software languages which have been adapted. So BlueSpec feels a lot more like you're writing real hardware. And so it's easier for a hardware engineer to think that way. And that's a huge force multiplier. Um, we use a lot of automation inside the team. We use continuous integration. These are all things which are learned from the software industry, not necessarily always deployed in the hardware industry. We use version control, which uh, endlessly fascinates some of the old generation hardware engineers, because we can keep track of very precise track of what's going on with our code. Uh, I can let people experiment a lot more safely. So there are force multipliers. So you don't need as many engineers as you think you would to build a chip.
Okay, interesting.
We did it with a team of like six.
That is a really
Yeah.
lean team. Amazing. Uh, if things go as per plan, how many chips would you sell next year?
Um, as per plan, the plan is still being worked out, but the target that I would like to reach is north of 2 million chips.
Wow. Okay. And
That's a
what?
small order.
Okay. Yeah, for a fab, it would be a small order, right? Like,
Yeah, exactly. That's a problem, right? We need to have, it's huge for us, but then for the fab, it's just, I don't know,
yeah, it's like 2 days
like an order
production.
of 100 wafers. It doesn't even cross decimal rounding error in the bottom of their Excel sheet.
Yeah, yeah. Mm. And how much revenue would that net you? 2 million chips. Selling 2 million chips would give you how much revenue?
Quite a lot. We haven't worked out the price exactly yet. We need to get quotes from the foundry and quotes from ATMP to actually narrow it down.
What is
But
ATMP?
assembly, testing, marking, packaging.
Okay, okay,
So we
right.
need to get those quotes, and a lot of that can only be fixed after the prototyping has been one successful run has been completed.
I mean, so those are the costs, but you have been in the market. You would know that I can sell this chip for $1 each or
Yeah,
$10 each.
yeah.
Just from that estimate, what kind of revenue would that give you?
Um, I really don't want to quote a figure right now because So the other side of the market is also important, right? What is it the market is willing to take? Now, if I can happily quote a TI price for this
TI is Texas Instruments.
Texas Instruments, and if I quote a Texas Instruments price, nobody will buy it. But then the revenue number will look really good because TI sells some of these chips for like $8, $10. So you're looking at 20 million in revenue. That's huge for a 3-year-old, 4-year-old company. But I mean, I can't quote a TI price, right? And there is a lot of value add. What exactly are the value adds that you're going to give with this chip, and how are you going to price those things? Pricing models, a lot of the pricing models are still up in the air.
So it's not a flat X dollars per chip, but there will be
There,
add-on
and
services.
the bigger volume that a customer gives us, the bigger the order I can place at the foundry, the bigger the order I place at the foundry starts giving me discounts, and I'll pass those discounts on to the customer.
Right. Yeah. Yeah. Hmm. Okay.
So,
Okay.
and the foundry, negotiating the foundry is exactly like negotiating with an auto wala at the railway station.
Yeah. Yeah. You have no choice. You.
You have no choice.
Yeah. You can address say bhaiya, please.
Yeah.
Okay. Interesting. Hmm.
So that's a very, I mean, it's that way for a reason. And the reason is that for the foundry, it's all about keeping their lines running 24/7. So if you give them a slightly larger order and say that you can keep it active for another 5 days, on purely on the basis of my order, then they're very happy to have that conversation. You're at scale already. I mean, the fact that you're talking to these big foundries is you're already at that scale.
Yeah. Okay. What would be the price differential between chip 1 and chip 2, just to understand
Um,
how much is the value add that is happening in chip 2? Like if chip 1 you were to sell, let's say $5 each, what would you be selling chip 2 at?
so I'll just take your $5 number. It's somewhere in the middle of the range where I would like to price it for chip one. Let's say then chip two would be in the $15-$20 range.
Okay. And who are the customers for chip 2? What is the use case there?
Security cameras is a big one.
Why is there a need for
Infotainment.
a specialized chip for security cameras?
Um,
I mean, what the,
not just security cameras, IP cameras. Let me be a little bit more broad on that. You can have industrial cameras, you can have baby monitors, all of them can use the same chip.
hmm,
Um, these devices need to take input from the camera, compress it really fast, and send it on. So they need speed for, and often today you have these event-driven kind of things where you don't record everything. You only pass on what is an event. So you need to have processing to read the camera, which is already quite fast. It's let's say even if it's at HD 30 frames per second, that's already one HD frame is 2 MB into 30 frames per second. That's 60 MB per second, MBytes per second
hmm,
uh, on a tiny chip. And then you need to compress that, like whatever MP4 or whatever. Mhm. And then you need to stream it to, if you're a security camera and you're a battery operated security camera in some godforsaken corner of a campus, you need to do that on a battery budget. And then you're streaming it, and then you're doing inference to see whether someone, I mean, like, I don't know, face detection, voice detection, something like that. You may have audio and you have to process the audio also. So, yeah, it needs its processing power. It's not,
so
and
you
yeah,
need a chip which is purpose designed to achieve speed
it's
and
not purpose designed to achieve for a security camera. It's purpose designed for computer vision workloads. And the thing about computer vision workloads is that if I design for CV workloads, then it's automatically equally well designed for certain other workloads. Like, um, I'm talking about putting it on a security camera. It can be used on the other side. It can be used on a TV. You're encoding here, you're decoding here. It's very similar kinds of workloads.
Okay, got it, got it. Whom did you raise this $2.3 billion from?
Um, we raised it. It was led by what was then Sequoia India, Sequoia Capital India, now called Peak 15 Ventures. We had two other VCs on the round and a couple of other angels. So Special Invest and Whiteboard Capital were on with us. And yeah,
Was there some amount of struggle story behind raising the fundraise, or was it relatively easy to raise? Or
um, well, I don't have first-hand account. I mean, experience of how difficult it has been for others. But then I'll just give you an example. I'll give you a timeline, and then you'll understand, right? We started talking to Sequoia in Feb 22. We signed the term sheet on August 15th, signed the SSHA in November, late November, and got the money in January.
about
One
11
year.
months? Yeah, yeah, almost a year.
One year.
Hmm, hmm, hmm.
And a lot of that, the initial phase, convincing people that this is something that you can do, this is something that you can believe in. And um, I'd say it's probably a little easier now, but you know, mm, the previous cohort of semiconductor and hardware startups from India had it really rough because nobody could believe that you could do hardware from India and you could do products from India. This is a very, very important thing. I mean, a lot of services people doing, like uh, for all the foundries, their process design kits are designed by our IT majors, HCL, TCS, Infi. A lot of Intel's, the Intels and AMDs of the world outsource to India. But I can own a product and I can actually build it from India is a story that not everybody was willing to believe. It's gotten a lot better over the last couple of years. I'd say since about 2020. It's gotten
Yeah,
a lot better.
India doesn't have a track record of hardware success as such. The track record is mostly software success.
And I would say that that's unfair because India has had some really brilliant early hardware successes. And it's just that we didn't follow through on that.
Which ones? Like,
Well, for example, in the early days, HCL had their own hardware division.
yes, they did. They had a PC.
Yes. And it's not just PC, they were doing servers, they were doing all kinds of stuff. They could have been a competition to, well, in those days, the Compacts and Dells of those days.
Yeah, yeah, yeah. I
Um,
believe HCL started as a PC company, right? The
yeah,
software was something they pivoted to, but
they
the origin
pivoted to
was,
software later.
yeah, yeah, yeah.
So HCL is one. Early HCL is a nice model to think of. We've had other hardware. Hey, for example, I mean, uh, think of Tata Motors. It's a hardware company for all. A modern day car is basically a computer on wheels.
True, true. Yeah.
The Tata Mahindra, they're basically computer companies. They may not do semiconductors, but they do hardware. Mm. There are lots of other companies under the radar which are actually supplying the big guys. You'd never know that these companies are Indian. And what happens a lot in the industry is that there are Indian startups that start and then they very, very, very early get acqui-hired by somebody else. And so again, that doesn't look like an Indian company anymore, but For all intents and purposes, it is. There's a
What
lot of
is
that going on also.
what's your role at Mindgrove?
My role at Mangrove. Hmm. And to begin with, my role at Mangrove was 50% of the work because there were just two of us. But one of the things that I'm definitely good at, and I know I'm good at, is delegating and letting people do their work. So my role at Mindgrove is to be the um, place where the buck stops. My role would be to. The other thing that I'm very good at is going in, taking a problem, looking at it, and immediately finding a solution, even if I haven't seen the problem before. So my role is on the engineering side. It is to provide guidance, to troubleshoot, to firefight, to solve problems. Um, we are still doing about like 80-85% of sales and marketing as founders, and that's what we've been encouraged to do by everybody. Is saying you need to do it at least a few times before you can guide somebody else to do it. So we're doing that. So I mean, we don't have very strictly defined roles. I call myself CEO, he calls himself CTO, but Sharon and I don't strictly define roles between the two of us. If there's an admin task and I'm not available, he'll take it up and do it. If there's a technology task and he's not available, even if he's available, even if I'm available, we might just take it up and do it because it's just easier to do it that way. It's something that I know and he doesn't know, or he knows and I don't know, whatever. So yeah, that's it's a very fluid kind of a role, and I like to keep it that way.
So, like, say, in a 10-year time frame, where do you see Mindgrove being?
Where we would definitely like to be is um, 4, 5, 6 established chips in the market. And I told one of my investors this. I'll know I made it when I open a product and I find a micro chip in there, and I something that I bought off the shelf somewhere. I find a micro chip in there, and I did not know beforehand that there was going to be a micro chip in there.
Amazing, amazing. More power to you in making that dream come true.
So that is my measure of success. All other things, I mean, mm, but it's very hard to predict exactly what kind of products we will build even 3 years down the line because the industry is changing very, very rapidly.
Hmm,
So uh, the technology is changing very rapidly. The industry is changing very rapidly. The way that we think about building certain things is no longer the same as it used to be,
hmm.
and we are looking to sidestep some of these technology ladders and just go straight to the not have to go through the route that some of our seniors in the industry had to go through. Just take the learnings and go straight to where we need to reach.